solution can be shown to be optimal. And then we talked about this duality theorem, which basically, tells you how the optimal solution can, in fact, how you can generate this proof of optimality in an automatic fashion. Now, what I want to do is I want to basically look at the simplex algorithm once again. Okay. So a good analogy for simplex algorithm is like a pebble falling down. Okay. So let's go back to our very first problem. Okay. So what is the pebble falling down analogy? So the idea is, suppose you take this picture, okay, and rotate it around so that our objective function, right, the line describing the objective function comes parallel to the ground, right? So now, and then let's say you put a pebble over here, and then you turn the whole axis down so that this line comes to the bottom, okay? So then the idea is that the pebble is going to fall because of gravity, and it's going to end in one place, which is the resting place that has the least gravitational potential energy, right? So that's basically what's going to happen. Or in our case, the gravity is going to be defined by the objective function, and the objective function is maximized at this point where this pebble is going to come to rest. Okay. So again, the point is just turn it around so that the line describing the objective function comes parallel to the ground, and then you let the pebble fall. Okay. So essentially what happens is that you start from the origin and the pebble slides, because obviously you want the pebble to stay within the feasible region, so it stays inside the polygon and it keeps sliding down on one of the edges, and then it reaches the vertex, then it changes direction and falls along the next side and so on until it reaches the bottom. Right? So this is how this is a very good way of understanding how the simplex algorithm works. Okay. Again, as I said, the only case where it's really interesting is where there is a unique point where the function is objective is maximized. So we'll just deal with only those problems, not under-constrained problems where there can be many optimal solutions. Okay, so the problem is easiest to understand when we think of two dimensions, right? Because we understand two dimensions. We think we understand three dimensions, but we, have some understanding. I think that's the best way to say it. Okay, and fourth dimension and our n dimensions, we have absolutely no idea what it means, right? Okay, so let's try to think about, and of course, when you have n variables, then the problem becomes n dimensional, right? So that I think most of you see. So essentially, what you have is a feasible space which is called a convex polyhedron in n dimensions. Okay. So now let's try to understand a few things. Okay. What is a line? Right? In n dimensions, what do we mean by a line? Okay, so how can we understand, what is our only tool for understanding, multiple dimensions? Right? The coordinate geometry, right? So we can think of any number of axes we can think of, and we can think of equations involving any number of, those dimensions. And the coordinate geometry doesn't become any more difficult or easy because you have, 2 dimensions or 6 dimensions, right? So the only tool we have to understand higher dimensions is coordinate geometry and these equations and so on, right? So let's think in those terms and try to answer the question, what is a line in n dimensions? What do we mean by a line in n dimensions?
An expression defined by 3 closed dimensions.
Any two. Think of it just in 3 dimensions, right? If I say x1 plus x2 equals 1, what will that be?
plane.
Now we're plane, right? So if I have an equation involving okay, so again, let's try again. What is a line? What is the nature of a line, right? What is the distinguishing characteristic of a line? Line is one-dimensional, right? So that is the most, of course all of you are giving the right answer, it's just that I am looking for one answer. So line is one-dimensional. So from that, what can you say? So what is a line in multiple dimensions? Once again, maybe I know what answer I'm expecting, and maybe there's no way for you to guess what the answer is. But the point is that on a line, I only have to specify one of the dimensions, right? If I specify x1, then you can immediately tell me what are the values of everything else, right? So that is the property of a line, right? If I tell you x1 equals 5, then you can tell me what is x2, x3, x4, x5. That is the whole point of a line, right? Because again, it's one-dimensional. So there is only one coordinate that I need to specify. Once I specify that coordinate, every other coordinate should be available, right? So again, that is the meaning of one-dimensional thing means, well, there is only one thing that can change independently. Everything else is constrained by that one dimension, okay? So a plane, what is a plane? So in n dimensions, what would I mean by a plane? So I think the problem is that when we go to n dimensions, we run out of names, right? So we only have line and plane and volume, right? Only three things. But obviously there are n things that we need to talk about, right? So what we end up doing is using overloading these terms. So we'll say hyperplane in the n-1 dimensions. Well, that means okay. Again, but the dimension aspect is clear. When I say n-1 dimensions, that means that if I specify n-1 coordinates, the nth coordinate is going to be fixed. Okay, so that's the meaning of n-1 dimensions. If I say k dimensions in n-dimensional space, what that means is that I need to only specify k of the n coordinates, and the rest of them will be fixed. Okay. So again, what is a vertex in n dimensions? So a vertex is a point where many of these inequalities or what we think of as lines, right, in two dimensions, they intersect, right? Okay. So again, you have to have n of them intersect because a vertex is a single point, so which means that you have to have n of those equations intersecting, and that's when you get a single point, right? Otherwise, you can again use your intuition about three dimensions, right? So if you have two planes intersecting, well, you'll get a line, right? You won't get a point, right? So if you have to have three planes intersecting, then you'll get a line, right? So that's why you have to have n inequalities in order to get a single vertex. Okay, and you can go along this line of thinking and then ask what is the neighboring vertex, and then you'll see that a neighboring vertex is one that basically shares n-1 inequalities. Okay, so at least even if you don't, some things you really have to think about it on your own, right? So I can't really make you understand in its entirety, but I can give you some at least examples in the familiar dimensions, right? So when I look at these two vertices, right, they share one inequality, which is this line, right? So these two vertices share this line as one of the inequalities. So we are talking about 2 dimensions. So n minus 1, sharing n minus 1 inequalities means sharing 1 inequality. And so you can see that, okay, that's what I'm doing here, right? 2 vertices, neighboring vertices means I'm sharing 2. Now I can also go down here, and then I can ask, okay, so what are these sharing? Well, these are sharing the surface which is the x1, x2 plane, right? So if you look at these 2 points, right, those are neighboring vertices, right? So I am sharing 2 planes. One is the x1, x2 plane, and then this triangular face is another plane, right? So again, n minus 1 here is 2. So I'm sharing 2 of those inequalities to get to the next vertex, right? So in general, you can see that, okay, so a neighboring vertex would be one which shares n minus 1 inequalities. Okay? So what I need to do is I need to say, okay, I am at this vertex which corresponds to the intersection of n inequalities. So I'm going to drop one of them, and then I'm going to try adding another inequality, and now this would correspond to a vertex that's a neighbor. You see how that's done? Right? So all I need to do is, okay, I am at a vertex which I know corresponds to these n inequalities. So I'm going to drop one of them, add one of them, and that's going to be one of my neighboring vertices. Right? So that's how I'm going to compute my neighboring vertices, and I'm going to evaluate the objective function, which is, of course, trivial, right? It's just an equation involving a bunch of variables. You can do that. Now the question is, okay, what is the complexity, right? Because how many vertices are there, right? We certainly know that the upper bound is the number of vertices, right? So because we're going to try vertices one by one. Okay, so how many vertices are there? Well, if you have m inequalities to start with, well, then you're going to add n more, which basically are saying xi greater than 0, right? So there are n inequalities that are added just to say, okay, each variable is greater than 0, and then there are the original m you start with, okay? So how many vertices are there? Well, m plus n, choose n, right? So you can choose any subset of n vertices, and that will correspond to a vertex, right, in general. So that is, of course, an exponential number, right? M plus n, you can see it's going to be m plus n factorial divided by n factorial whatever, right? So once you see factorials, you can see it's exponential, right? So there are an exponential number of vertices where it's exponential in the number of constraints, right? So if you have m, right, so it's exponential the number of constraints and the number of dimensions. So as a result, simplex algorithm is actually an exponential algorithm in the worst case, but turns out that in practice it works very well. So people end up using it, continue to use it all the time, even though the worst case complexity is exponential. Well, okay, so this is trying to illustrate the simplex algorithm on a picture, but I think we have done enough, and we don't have to go through this. Let me just end this discussion with the discussion of some history. So linear programming was, began in the 1800s. So the same person who thought of Fourier transformation, thought of this in the first place. But really, it started being used as a tool, optimization tool, really in the 1930s and 40s. In 47 is when the simplex method was discovered, and a Nobel Prize was handed out for linear programming, and you'll see that interestingly, the computer scientist is, of course, not the recipient there, right? So the people who are so obviously there's no Nobel Prize in computer science, right? It's only in economics. And economics, well, if you are a pure computer scientist, you're not going to have much credibility as an economist. So obviously the people who are economists are the ones that get Nobel Prize. So as we said, the simplex algorithm itself is exponential, and so people wanted to, and there was a question whether linear programming is it's an NP-complete problem or a problem that requires exponential algorithms or they're polynomial algorithms. And it turned out that in the late 70s and early 80s, people found actually polynomial time algorithms. Okay? And the first algorithm is polynomial, but is, in practice it's expensive enough that nobody uses it. The Kramarker algorithm is good in practice as well, although it's not the case that still simplex works so well for most practical problems that you'll see simplex being used very often. But there are times when the simplex is takes forever, and the Kramarker algorithm sort of fills in that gap. And you can see that if you want to make name for yourself in this domain, well, obviously your last name should start with a K, right? Otherwise, you might as well look for some other area. Okay, so what I'm going to do here is, take a few minutes to talk about do we have the midterm papers?